Okay, this is a continuation of our algebra of functions. This is going to be a continuation of the algebra of functions. And specifically here we're going to talk about the domains of the algebra of functions, or the composition of more than one function whenever you add, subtract, multiply, or divide them together. And I will do an example of what most textbooks like for you to do when it comes to identifying the domains of functions. However, I tend not to emphasize their methods. They tend to be a little too formal. They tend to take a little too much time, when in reality I can find it easier to look at my final function and determine the domain rapidly based off of the final composition, or the final addition, subtraction, multiplication, division. So let's go through and just look at an example. Let's just look at an example. So let's say that I have f of x, and we're going to say this is going to be equal to square root of x plus 4. And well, actually we'll use x plus 3 because I've used x plus 4 before. So let's go ahead and try g of x. And this is going to be equal to negative 2x plus 5. So what they want you to do here is that they say, okay, you know what? Let's determine f of x. Let's find the domain of f of x. And the domain of f of x, since it's a radical function with an index value of 2, and when we don't see the index of the square root, we know it to be a value of 2. We recognize that the radicand, x plus 3 must always be greater than or equal to 0. Subtracting 3 on both sides, we know x must be greater than or equal to a value of negative 3. That's a negative 3, a negative 3. We can write that in set notation as a set of x such that x is greater than or equal to negative 3. Or you can write that in interval notation, which would be negative 3 to infinity. And over here we can find the domain of g of x. And hopefully we recognize that g of x is in fact a linear function, which is a type of polynomial. So therefore we know his domain to be all real numbers. So we could write that in set notation as a set of x such that x exists as all real numbers, or in interval notation starting at negative infinity going all the way to positive infinity. Remember, we never include infinity, negative infinity in our intervals, so it's always enclosed with parentheses. If you have to look at this and it's not clicking for you in terms of their domains, go back and watch some of my videos about how to identify rapidly domains of different types of functions. This is a polynomial. G of x is a polynomial. So you will look at that, and then f of x is a radical. So this is going to be a radical function. So keep that in mind. So let's say now that we want to find we're going to find f plus g of x, and then we're going to find f minus g of x, and then we're going to find f times g of x. So we're going to find these three and domains. So and its domains. So f plus g of x, we're going to have the square root of x plus, let me split this up. So this will be f of x plus g of x. This will give me square root of x plus 3, which is f of x, and this is all underneath the radical, then minus separately 2x plus 5. The f minus g of x, I like to write, making sure I do not forget to distribute that negative to my second function. So I'm going to have the square root of x plus 3 minus the quantity of 2x plus 5. And that's going to be equal to the square root of x plus 3 minus 2x minus 5. And then here, this doesn't even look very nice, but we're just going to have f of x times g of x. So we're going to be multiplying these functions together, and that's going to give us the square root of x plus 3 times negative 2x plus 5. You can't really simplify that, so I'm going to leave it just like I see it. When we want to evaluate the domains, so let's write a little note here: in order to evaluate the domains of f plus g of x, f minus g of x, and then f times g of x, their domains will be the intersection, of the domains of the independent functions. It's a really nasty way of writing independent. Let me erase that. Independent functions. So let's just look. So let's go ahead and look again. So I have the domain here of f of x, which is x must be greater than or equal to 3, and then negative infinity to positive infinity. So if we want to find their intersection, we recognize that intersection is synonymous with overlap. Where does this overlap? Where do the two domains overlap? So let's go ahead and draw a number line. And we had our first domain that was x such that x is greater than or equal to a value of negative 3. And then we had our second domain, which were all real values. So I wrote that in two different notations. Let me just go ahead and, there you go, exists. And this one will be negative 3 to positive infinity. Oh, and then we're going to have to include negative 3 because it's greater than or equal to. I'll make sure that is correct. And that is correct. So now what we can do is that we're going to plot them on a number line. So I got 0, then I got negative 3. And I'm going to use a bracket opening to my right. And I have an arrow pointing to the right. Negative infinity to positive infinity means that I'm going to have an arrow that runs along the number line, and intersection and mean the exact same thing, and it's just where do these guys overlap, and they overlap where I'm highlighting in yellow. That's where they're overlapping, and we see they overlap from negative 3 to infinity. You could say the domain for each one of these guys is all going to be, the domain for each one of these guys is going to be x such that x must be greater than or equal to negative 3. Or you can look at the final. You can look at the final addition, subtraction, multiplication, division. Each one of these has that radical in it. So if you look at the final function, whether or not you've added, subtracted, multiplied, or divided, add, subtracted, or multiplied, a division is slightly different. All you have to do is recognize that the radical populates in each one of them. So you would see the exact same issue. This part is polynomial. This part is a radical. This part is a radical. This is the polynomial again. Then we have the radical, and here's the polynomial. So that radical's domain will trump the polynomial. So that's the reason why we will always have to look at it, or we could perform this analysis on a chart, on a number line, I mean. So what happens when we want to divide? When we divide, the domain will still be the intersection of the domain of f of x and g of x. But we're also going to add that g of x can never equal to 0, because in that definition that we talked about in our last video, that the denominator can never equal to 0, so we're going to have to exclude whatever values cause your denominator to equal to 0. So again, our functional value at x was equal to that square root of x plus 3 and negative 2x plus 5. So square root of x plus 3 and g of x is equal to negative 2x plus 5. Again, their domains independently have not changed. They have not changed. So this domain is still the set of x such that x is greater than or equal to 3. And this domain is still going to be all real numbers. But we know that our denominator, and it might help for you just to go ahead and set f divided by g of x equal to f of x divided by g of x, and according to us that will be square root of x plus 3. Notice that radical is populated one more time, but now in our denominator we have negative 2x plus 5, negative 2x plus 5. So we know that when we overlap these, or when we find where they intersect, we're going to have to exclude a value. And we have to exclude wherever our denominator equals to 0, because negative 2x plus 5 can never equal to 0. Solving this on both sides, we have negative 2x cannot equal to negative 5. Dividing both sides by negative 2, we get x cannot equal to positive 5 halves. So now when we look at this intersection, we're going to draw all of these simultaneously. So let's go ahead and draw all of these simultaneously. So on our number line, I'm going to indicate that I have 0 and then I have this negative 3, and this still gets a bracket opening to the right. The second one of all real numbers, which comes to the polynomial, looks like this, so we're still seeing that overlap. But notice here at 5 halves, which is 2.5, we have to exclude this value. This value cannot ever exist. It has to be excluded from our domain. So if we have to exclude it, we are going to eliminate this value. We're going to eliminate this value. So we're going to eliminate it by adding a set of parentheses here and a set of parentheses here, parentheses because we can't include it, and a set of parentheses here and a set of parentheses here. So now we recognize, where do they overlap again? They overlap from here to here, and then they overlap from here to here. So this would be much easier to write this domain in interval notation. So we're going to start at reading left to right. Wherever we have that yellow overlapping highlight, we're going to have negative 3 to 5 halves. We include negative 3, but we do not include 5 halves. Then we have to union or conjoin this, starting at 5 halves, going on to positive infinity, not including 5 halves and not including infinity. So the domain of f divided by g of x will in fact be that guy.